Sorry. All right, next door, can you hear me? Thank you. Okay, so before we get going, did anyone go to the Math Union revision thing yesterday from 4 till 6? Any good? Well, no, you were there. Anyone else? Did people go? Did you have a good turnout? Was it a good turnout?
More than 40 people, I think.
Sorry?
More than 40?
40?
Yeah, a bit more. I think it was 40.
Okay. All right. Well, yeah, you'll do that for test 2 as well, right? And it was for 1011 and 101.
I'm not entirely sure about it. Yeah, it was from 111 and 112.
Yeah.
I'm not entirely sure what features, but I'll...
Okay, cool. Oh, yeah, anyway, I hope those who went got some use out of it. Now, so what we're covering this week is how we find maxima and minima of functions of several variables. The hard ones are where we've got to find global extrema. So you remember I went through this example. If you can do this one and understand this one, you've nailed it basically, right? So because this question sort of brings it all together. So if you haven't had a chance yet, please do work through this example because this brings it all together. Now, as I explained, all we've done so far is locate the critical point. So the way we locate the critical points is very similar to what we do with a function of a single variable. Function of a single variable, you find the first derivative, set it equal to 0, solve for x. Same thing here. Now we have a function of two variables, there are two first order derivatives, you set them both equal to 0, you solve for x and y. The catch is that the equations will very rarely be linear, and sometimes they're coupled, which means x and y appear in both. So the hardest part often with these problems is figuring out how to solve them. So the best advice is, it's a skill that comes with practice. I can't sort of give you any hard and fast rules about what's the best way to go because it totally depends on the function and the question. You just have to, my advice is when you're solving these problems, you write down the two equations you've got to solve and then look at them, right? And just think what is the best way to attack them, right? And it will change depending on the question, right? Unless I royally stuff up though, because there will be plenty of things where you can't, there's lots of nonlinear equations we just can't solve. Like a classic, even simple things like, there are lots of things we can't actually solve. So a classic one is, solve that for x. You can't. I can, but you can't, right? I can because it involves a function you've never heard of. It involves something called the Lambert function, which is not something you'll certainly see in first year, but there's lots of equations that we can't solve. One that actually cannot be solved at all. That can't be solved. No, you have to do it numerically. So, but of course, when I set you these problems, I check very carefully I have not accidentally given you one that's impossible, right? Because I have done that in the past, right? And it's extremely embarrassing. But the point is that as long as I don't stuff up, if you get something, it's solvable somehow, right? The somehow is the hard part. The other thing is we haven't gone through classifying them yet, and as I explained, there is no concept of a first derivative test for a function of several variables because, unlike a function of a single variable, when we've got to check the derivatives, we've only got two sides to check. A bit like the limit problem. For a function of a single variable, there's only two limits to check. Function of two variables, there's infinitely many limits to check, and we can't check them all. It's the same for a function of several variables. There's no equivalent of the first derivative test because we can't check all the possible directions. So we only have a second derivative test, which is the last thing we're going to cover. Now, the other problem is, unlike a function of a single variable, the second derivative test makes sense. The second derivative's checking concavity, right? Function of several variables, the second derivative it's kind of telling you what the concavity is, but the concavity in infinitely many directions. It's not intuitively obvious why the second derivative test for a function of several variables work. And unfortunately, I can't prove it to you either, yet, right? Because it involves a matrix, and you need to know what eigenvalues and eigenvectors are. So those of you doing 101-2, you wouldn't be up to eigenvalues, would you? Anyone know what an eigenvalue is? Right, then you're probably, one person does. You're probably not there yet, right? But next week we're going to do something called Taylor series. And I can give a very it's in the unit reader. There's a very hand-wavy proof, not rigorous, but it gets the idea across why this works, why this test works. But we can't do that till we do Taylor series. So this is one of those things where you have to just take my word for it. All right? But we only have the second derivative test. And just like the second derivative test for a function of single variable, the catch here is it can fail. But unlike the single variable case, if it fails, you say it fails. And if you really want to know, then you could plot it, or we have no first derivative test to fall back on. But let's go through the process of the second derivative test. And this is actually the first thing that's on the formula sheet. So you do not have to memorise this, right? This is actually the very first thing that's on the formula sheet. And you see, it's an algorithmic test, just like function of a single variable. Function of a single variable, you have to calculate the second derivative. If it's positive, you've got a minimum. If it's negative, you've got a maximum. If it's zero, it fails. It's the same thing here. There's just more things to check, right? And it's not, unlike a function of a single variable, it makes sense. Again, the way I remember it is x squared, second derivative is positive, it's a min. Minus x squared, the second derivative is positive, negative, it's a max. Right? The function of several variables one is not really intuitively obvious why it works, right? But I'll try and explain why it works. Right, so let's say we've got a function of two variables. Recall that obviously everything we do can be differentiated infinitely many times. So here we need the second derivatives. And recall also, of course, that always every single function we visit in this unit, the mixed second order derivatives are equal. The only time they're not equal is for very weird functions that we're not going to see in first year. Then we create this matrix. It's kind of like the second order version of the determinant matrix, right? So remember the determinant matrix, the Jacobian matrix, right? So remember the Jacobian matrix is a summary of first order derivatives. This, which we call the Hessian matrix, Hessian is a person, just like Jacobian's a person, is a matrix summary of second order derivatives, right? And it's for a function of two variables, the Jacobian matrix is a 1 by 2. This is a 2 by 2, right? And note the order. The order, we can't stuff this order up. Right? The top left is second order partial derivative with respect to x. The bottom right is the second order partial derivative with respect to y. And then the opposite diagonal ones are the mixed ones. And of course, these two must be equal, right, for all the functions we're dealing with. So we basically construct this matrix, which we call the Hessian matrix. Sometimes we use a similar notation. The Jacobian matrix is d of f. The Hessian is sometimes d squared of f. It's a matrix describing the second derivatives. The crucial thing is that the second order partial derivative with respect to x must be the top left. Right? When you do more of linear algebra in 1012, those of you who are doing it now or doing it next semester, you'll find that a lot of the properties of a matrix is determined by the sign of the entry in the top left spot. Right? So it's crucial that that's where we put partial d squared f dx squared. Okay? Since it's square, it's got a determinant. Right? Top left times bottom right minus top right times bottom left. And of course, top right and bottom left are the mixed partial derivatives, they're equal. So all these three formulas are equivalent. Right? Once I've got the determinant of this Hessian matrix, I can then say what the second derivative test is. So then we have the second derivative test. Suppose we've got a function, it's got all of its second derivatives, and we've found at some points where the gradient vector is 0. So we've found some critical points and we want to classify them. We create the Hessian matrix and calculate the determinant. You can do this two ways. You can either do this as this matrix and the determinant as a function and then plug in x and y, or if you prefer, you can plug in all your critical points first and then do this. I'll show you what I mean with examples. Right? If it turns out, now even I have to look these up, right? That's why this is on the formula sheet. You don't have to memorise this. If the determinant of the Hessian is positive and the partial derivative, second order partial derivative with respect to x is positive, then we have a minimum. Right? And that's kind of like second derivative positive function of it's a minimum. Right? But these two things have to be positive. The determinant and the top left entry of the Hessian matrix. If the determinant's positive and the top left entry of the Hessian matrix, which is the second order partial derivative with respect to x, is negative, then we have a local maximum. Right? So for the first two, there are two things to check the sign of. If the determinant is less than 0, then no matter what sign the entry in the top left is, we say that is a saddle point. Right? In other words, it's neither a max nor a min, but we don't do any further investigation. There's no sort of concept of an inflection point and things like that for functions of several variables. And just like for a function of a single variable, if the determinant is 0, the test is inconclusive. Right? Now, for a function of a single variable, when the second derivative test fails, we go back to the first derivative test. We don't have a first derivative test here, so if it fails, it fails. And so the answer I'm looking for is test fails. Right? Now, again, to prove this, because this does not seem at all obvious, does it? Right? It's not like a single variable one where it makes sense. If you think about it, it makes sense. This one doesn't yet. There are two ways I can prove it rigorously using linear algebra. There's no point showing you that because most of the class hasn't done linear algebra yet, right? Because that's what you'll do in 1012. There is another way where I can give a hand-wavy proof, but I need Taylor polynomials for that. That's what we're covering next week. And it's in the unit reader. It's at the last thing in the Taylor polynomials chapter in the unit reader, if you're interested. I'll talk a bit more about that next week. So this is one of those things you just have to believe me. Right. Let's have a look at an example. But you'll see it's very algorithmic. Right? Find all the critical points of this surface, right, and determine their type if possible. Right? So in other words, if not possible, the test fails. Right? Now, so I find the gradient vector. Basically, I just find the first order partial derivative with respect to x and y, and I solve them. Remember, this is the hardest part, generally. Right? What have we got here? The first equation is basically saying y equals x squared, and the second one is saying x equals y squared, isn't it? That's basically what it's saying. Right? So you have to solve those two carefully. here I've plugged y equals x squared from the first one into the second one, so the second one basically becomes minus x plus x squared all squared equals 0, getting rid of that common factor of 3. Basically, x to the 4 minus x equals 0, factor it out, so either x equals 0 or x equals 1. Right? So therefore, y is 0 or y is 1. So we've got 2 critical points. Remember, the critical point's got to satisfy both. So we've just got the point 0, 0 and 1, 1. Right? Now there are 2 ways we can go, right? Depending on which way you prefer and which way you find easier, less prone to a mistake. I need all of the second order partial derivatives. So they're easy to find. I find second order derivative with respect to x and y. I find the mixed ones both ways. That's a self-consistent check, because if they're not equal, I've stuffed up. Something's wrong. Right? But here I just get minus 3. Right? Now, at the point P1, which is the point x equals 0, y equals 0, my Hessian matrix is 0, first row 0, minus 3, second row is minus 3 and 0. And I find its determinant 0 times 0 minus minus 3 times minus 3. As always, careful with the signs. The value is meaningless, just the sign is important. Right? Just like the second derivative test for a function of several variables. The determinant's negative, so I pull out my formula sheet, which has this on it, and I look, oh, that's case 3, done. So 0, 0 is a saddle point, finished. At the other point, at x equals 1, y equals 1, I calculate the Hessian, in this case, is 6 minus 3 minus 3, 6. Oh, sorry. Sorry. Sorry about that. Right, so this has determinant 27. So then I pull out my formula sheet. It's case 1 or 2, so I need a second piece of information. I also need the sign of the second derivative with respect to x. Basically the entry in the top left. So we can see that's case 1. Right, so that one's a minimum. So you see, it's very similar to just more, like everything with functions of several variables, just more work. Right, and we're done. Right, and if we plotted it, this is what it looks like. So the point 0, 0, which we discovered is a saddle point, is basically sitting here. And what you can see by saddle point, we mean it's in some directions it's decreasing, some directions it's increasing. Right, so you can sort of see, if you imagine, actually this is a better picture of a saddle point. This is, right, looks like a saddle. We're a real imaginative bunch, right? But you see, it decreases certain, right, so it's a saddle, that's what we just call a saddle point. And that's basically what's happening at this point here. Whereas at the point 1, 1, right, you would see it's like a trough, right? It's definitely a local minimum, okay? Now, as I explained, there are 2 ways to go. You could either do it where you calculate the Hessian matrix at the point and its determinant, or if you're confident enough, you can actually calculate these as functions. So let me show you what I mean. And so there's an example here. All right, we've got to locate and classify the critical points of this one. Now, this is one of the critical points ones I did talked about yesterday. Again, we've got to be careful how we solve, because there's a case that only satisfies one of the partial derivative. So you can see here the partial derivative of f with respect to y is 0 when x and y are both 0, but the first one isn't. So that's not a critical point. I don't care about that one. All right, and so this one we find 4 critical points. Now what I do is I have to construct the Hessian matrix and calculate everything at these points. Now there are 2 ways you could do this. You could either do it like here, right, plug in the point, then find the Hessian, then find the determinant, right, and do that for every point. Or, which is the method I prefer, is just calculate the Hessian and its determinant as a function. Right, so I don't plug the points in yet. Right, so I calculate the Hessian, the second order derivative with respect to x, top left, y, bottom right, and then the mixed ones, top right and bottom left, and calculate its determinant as a function. Right? So top left times bottom right minus top right times bottom left. I find this is just 36x squared minus 36y squared. And of course, I may need the sign of the the second order partial derivative with respect to x, the top left entry, so I've written it there. And then I check each point manually, right? So when x is 1, y is 0, this is, its value is, if you just wrote greater than 0, fine. Right? Its value is meaningless, only its sign matters. All right, so the determinant's positive. Then I look at my formula sheet, which has basically got these 4 things on it. So I'm in case 1 or 2. So I need an extra piece of information to decide. The second order partial derivative here is negative, right? So that's this case. It's a max, local max. Next point, positive, positive, min. Next point, negative, saddle, immediately. I don't need the second order partial derivative with respect to x. So notice this one just says that, right? Negative. And then at 0 minus 1, we also get it negative. So, right, see, it's very algorithmic. And the fact that I give you the things on the formula sheet, right? You don't have to memorise these things, you just do it. Okay. All right, and here's another one where I've written the x rather oddly, but anyway. Find the location. Right, so here I've got, what do I get? I've got partial, basically that equation says x squared equals y squared. What is this one saying? Y times x minus y squared has to equal 0. Right, so if I look at the first one, this one's telling me either y is 0, which then implies x has got to be 0 from here, or x minus y squared equals 0. I know x squared's got to be y squared, so this is the same as x squared. Remember, the way we solve this is not unique. You don't have to do it like me. That's the other great thing about nonlinear mathematics. There's usually several ways to do it. Right? Discovering which way is the best way to do it is a skill that comes with practice. But essentially, we find 3 pairs of critical points. So I find their type, I construct the Hessian matrix and its determinant, and keep track of my expression for the second order partial derivative with respect to x, because I may need it. And then I just check each point. Right? And I mean, you don't have to factorise this thing. I've just done this to make life easier. At 0, 0, I get the determinant 0, test fails, end of story. Right? No first derivative test to fall back on here. At 1, 1, determinant's positive, second order partial derivative with respect to x is negative, max. Next one, positive, negative, I get another max. Right? And that's how we do it. Right? As I say, the hardest part is actually finding the critical points in the first place. And as I say, it's a skill that will come with practice. Okay? Yeah, and most importantly, you don't have to memorise this. I mean, if we have a look at the formula sheet, I mean, you are getting the entire formula sheet for the test on Saturday, but this is basically the first, I give you this. Right? You don't have to memorise all of this. Okay? Right, but you see, it's very algorithmic, just like a function of a single variable. Okay? All right. Well, please do work through those examples. Now, I finished early for a reason. Anyone got any questions about the test on Saturday? All right? I'm here. Anything at all. Remember, don't, if you're struggling with something from the sample test, most likely everyone else is too. Don't be afraid to ask. Yes?
Can you give us any questions as an example? Question 7.
No. So question 7, it will not be, you'll notice on the practical sheets, some of the last couple of questions in the conceptual understanding thing get a bit hairy algebra-wise. It ain't going to be like that, right? It's basically we'll be testing your understanding of what we've been doing as opposed to rote learning, right? If you're stressed about it, don't. Remember, it's only worth 5 marks out of 25. It's better that you answer 6 questions well than 7 questions poorly, right? So only do it if you've got the time. Right? And you're confident that your first 6 questions are okay. I've told you what the first 6 questions are going to be. First question is something to do with limits of a function of a single variable. Second one's something to do with limits of functions of several variables. Third one's L'Hopital's rule. What's the fourth one? Vector functions. Fifth one's partial derivatives, tangent planes, 6 ones Jacobian matrices and Jacobians. Right? Then the 7th will be something, but remember the 7th will only be from the first 3 weeks. Yes?
I think I saw that in the practice test it was 30 marks. Is that about the marks?
It'll be the exact same number of marks. Is it 30 or 25? Right, sorry, it is 30, and so the last question's 5. I could have sworn it was 25. Yeah, don't get excited. Yes, 30 marks, right? And also please make sure you mark your practical class. It makes my life much easier when I've got to hand them back, right? So, any other questions? Let's get rid of that. All right, any other questions? Anything at all? Something in the sample test you weren't sure about? Yes, here we go.
In, I think it was question 5.
All right, settle down, settle down.
In question 5, it was like, in the solutions, there's one point where it's like 1 over sec squared.
Question 5.
Question 5. No. 4. 3. Yeah.
This one?
The 1 over sec 2 sec squared.
Okay. Yeah, I've had a few questions about this one, right? So let me go through this one and show you what I'm doing, right? So this one, right, you've got to use L'Hopital's rule to find this limit. Now remember what I said about L'Hopital's rule. If you can simplify things, right, it makes your life easier. But yeah, because if you miss it, you might have to do more work unnecessarily. So the first thing I do, you must identify the type, right, to get full marks, right? Because you've got to check that the conditions of L'Hopital's rule exist before you can apply it, right? So this one, obviously, I get a 0 divided by 0. So what I do is I differentiate the top, differentiate the bottom. Now, when I clean that up, I get to there. Now, what you could do from here is say, well, when I plug in x equals 0, I get a 0 divided by 0 again. And you could apply L'Hopital's rule a second time. However, I noticed that I can shortcut that by doing a trick, right? Now, basically, I know that when sec is 1 on cos, right, and of course cos is 0 is 1, so the sec squared bit, x squared bit down the bottom, as x goes to 0, that just goes to 1, right? So if I rewrite this thing slightly, and I pull that bit out, right, basically, you often use the limit laws without thinking. The limit as x approaches a of f times g is the limit of x approaches a times f times the limit of x approaches a times g, provided they're not 0 or blowing up. Right, so I pull that bit out and I can take the limit as x goes to 0 of the first bit straight away to give me a half. Right? Which is where that half comes from. Right? And this bit I can break this up because this is the fundamental trig limit. Right? So the limit as x goes to 0 of sine x on x is 1. Now if you miss that, that's fine, right? But what would happen in that case, let's say you didn't spot that. Right, let's say you got down to... Oh yeah, right, thank you. Let's say you got down to this. I mean, as long as you follow the rules of L'Hopital's rule, it'll work, right? It will keep working, right? The only thing to be aware of is if the type switches, that's a good sign something's up, right? And what I mean by that is we started with a type 0 on 0. Let's say if this was type infinity on infinity, that's probably a sign something's up, right? Because the type shouldn't switch. It might occasionally, but most of the time it won't. But as x goes to 0 and I basically get 0 on the top, I get another type 0 on 0. So I could apply L'Hopital's rule again. The problem is differentiating the bottom is not pleasant, is it? But it can do it. Please don't do it as fast as me. Right? And even I do not know the derivative of sec off the top of my head. Right? I'm loading the formula sheet so I can have a look. Right? I don't remember that one. That's why I've got a terrible memory. So the derivative of sec is tan times sec. So if I applied L'Hopital's rule again, and again, please don't do it as quickly as me. So the derivative of the top, let me just do it, then explain what I'm doing. Plus don't do it as quickly as me. And hopefully that's right. Right, so what I'm doing is the derivative sign is cos, the derivative of x cos x, that's a simple product rule. Right, so second cos x times the derivative of x plus x times the derivative of cos x. Now the bottom bit I've got to use a combination of the product rule and the chain rule. So I imagine it's 2x times sec squared x squared. So it's sec squared times the derivative of 2x, which is 2, so that's the first term. Get the easy stuff out of the way. Right, and then the next one is 2x times the derivative, sorry, I didn't mean to swear. 2x times the derivative of sec squared. So the derivative of sec squared is 2 times sec of x squared times the derivative of sec of x squared times 2x. Hang on. So that should be, hang on. So it's 2x times 2, that's an 8. 2x times 2x times 2, so that's 2x, so that's 4x squared times 8x squared, sec x squared 10. Right. That's about right. Now you could plug in x equals 0 again. All right, same answer as before. All right? Nasty one. All right? So in the solutions, I've made it easier by using the limit laws. All right? Does that make more sense? Yeah. And again, if you didn't miss that, you'd have to do all of this. And if this was the actual test question and you stuffed that derivative up, I would be kind of lenient. Right? This is actually a nasty question. So let me put it this way, your L'Hopital's rule 1 is not this bad. All right? Any other questions about the test? Yes?
So there's no so why so to be completed?
No, there's no so, because you got the test on Saturday, there's no so-or-so this Sunday. Right? Your next so-or-so one will be due next Sunday. Any other questions? Yes? All right, keep quiet please. Yeah, yeah. So only use L'Hopital's rule if you're getting indeterminate forms.
I mean like the limit of x over y equals the limit of x over the limit of y.
Oh yeah, most of the time we do it without thinking, yeah. Right? We just do it,
yeah.
Right?
And for that case, is it ended up with the limit of h as h equal to 0 on the bottom?
Yeah.
So whatever over 0 has.
Yeah, that's where they don't work, where we have to be careful. And that's what L'Hopital's rule does. It lets us be careful. Yeah. All right, any other questions? Well, I'll hang around for a few minutes if you want to come and ask me anything one-on-one, okay? Other than that, I will see everyone on Saturday, okay? Just let me unlink first. Yes.